Closed-loop design has become a central framework in regenerative urbanism because it shifts planning from minimizing harm to actively restoring ecological cycles within cities. Rather than treating water, materials, or energy as linear flows that enter, are consumed, and leave the system as waste, closed-loop districts emphasize continuous circulation where resources regain value through reuse, transformation, and biological processes. This shift is crucial as cities navigate increasing climate pressures, hydrological instability, and resource scarcity. From a multidisciplinary urban planning and design perspective, closed-loop design reframes the urban fabric as a metabolic network where built form, open space, and infrastructure co-evolve. International case studies demonstrate that successful regenerative districts integrate hydrological logic, ecological performance, and governance mechanisms that support long-term stewardship. By analyzing examples across three spatial scales, macro, meso, and micro, we gain insight into how cities can cultivate self-sustaining systems that reduce external dependencies while strengthening biodiversity, social resilience, and ecosystem function. This chapter explores closed-loop district design through a structured review of real-world case studies organized into macro, meso, and microscale systems. The text begins with foundational definitions and principles that explain how regenerative districts function as circular metabolisms. Next, it examines macro-scale examples: Amsterdam, Portland, Singapore, Hammarby-Sjöstad, Kalundborg, and Utrecht, each illustrating district-wide infrastructures that circulate water, energy, and materials. The following section focuses on meso-scale rainwater systems such as infiltration basins, trenches, retention and detention ponds, bioretention cells, bioswales, and riparian buffers across European cities. These examples highlight how neighborhood-scale NBS restore hydrological function and microclimate performance. Finally, micro-scale interventions, including extensive and intensive green roofs, showcase building-level systems that contribute to district-wide loops. Comparative insights, design implications, and a concluding synthesis close the chapter. This structure mirrors the presentation and ensures that each slide corresponds to a clear, coherent paragraph. The aim of this chapter is to help students understand the concept of closed-loop district design and its relevance within regenerative urbanism. By working through macro, meso, and microscale case studies, learners gain the ability to evaluate how resource flows, particularly water, energy, materials, and organic matter, shape urban metabolism. Students will learn how nature-based solutions, NBS, function as engines of regeneration by stabilizing hydrological cycles, improving biodiversity, and enhancing microclimate performance. A further objective is to identify design strategies transferable to landscape architecture practice, emphasizing systems thinking, multifunctionality, and long-term stewardship. Recognizing governance and community participation as essential components of closed-loop performance is also a key learning goal. By the end of this topic, students should be able to assess real-world districts, understand their regenerative mechanisms, and develop design proposals aligned with circular urban principles. Closed-loop district design also reshapes how urban systems are evaluated. Instead of measuring performance through isolated indicators, such as drainage capacity or energy efficiency, closed-loop approaches use system-level metrics that capture the interactions between water, soil, vegetation, materials, and human activity. This means assessing how quickly water re-enters the local hydrological cycle, how many materials circulate without becoming waste, or how vegetation contributes to evaporative cooling and biodiversity continuity. Closed-loop districts emphasize ecological reciprocity, where urban systems and natural processes co-benefit rather than compete. This theoretical shift encourages designers to treat urban space not as a collection of discrete objects but as a continuous metabolic landscape. By reframing districts as living systems, closed-loop design opens new possibilities for integrated planning across infrastructure, architecture, and landscape. Moreover, this expanded evaluative framework requires multidisciplinary collaboration and long-term monitoring. System-level indicators such as soil carbon content, groundwater recharge rates, habitat connectivity, material circularity scores, and microclimate performance become essential tools for understanding whether a district is truly regenerating ecological capacity. Closed-loop design also invites temporal thinking. Success is measured not only by immediate efficiency gains but by the system's ability to evolve, adapt, and produce cumulative benefits over decades. This perspective positions urban districts as dynamic ecological infrastructures rather than static built environments. As a result, planners and designers must anticipate how interventions interact with seasonal rhythms, climate projections, and community practices. The emphasis on circular flows and ecological feedback loops ultimately encourages more thoughtful, context-responsive decision-making that aligns urban development with long-term planetary health. Several core principles underpin closed-loop district design. Circularity requires minimizing leakage by capturing and reusing flows locally, transforming stormwater from a liability into a resource for infiltration, evapotranspiration, and cooling. Nature-based solutions act as systemic drivers, enabling soil regeneration, ecological connectivity, and climate moderation while simultaneously delivering infrastructural performance. Multiscalar integration is essential. Macro-scale district systems depend on meso- and micro-scale elements to function effectively, and vice versa. Governance structures must support adaptive management, aligning municipal authorities, private actors, and community groups. Long-term stewardship, whether formal or volunteer-led, is crucial for maintaining ecological performance. Finally, regenerative districts must demonstrate positive ecological outcomes, measured through indicators such as biodiversity richness, infiltration rates, material circularity, and microclimate improvement. These principles form the basis for evaluating the case studies that follow. Macro-scale closed-loop systems also illustrate how long-term planning frameworks shape regenerative capacity. These districts reveal the importance of aligning infrastructure investment cycles with ecological goals, ensuring that stormwater networks, energy grids, and material management systems evolve coherently rather than in fragmented sequences. The macro scale is where cities test governance innovations, such as circular procurement, integrated permitting for NBS, or cross-departmental performance targets. For example, Amsterdam's material passport approach only succeeds because institutions maintain digital infrastructure, regulatory pathways, and partnerships with developers. Similarly, Singapore's water cycle integration succeeds as a national priority involving legal instruments, education programs, and public communication strategies. Macro-scale systems therefore demonstrate not only technological innovation but also the governance maturity needed to sustain closed-loop performance over decades. This level of integration provides the structural backbone for meso- and micro-scale systems to function effectively. Amsterdam's Circular District Strategies center on reducing extraction and waste through reuse cycles embedded in building materials, water systems, and energy networks. The city's Circular Strategy 2020-2025 promotes material passports that track components for future reuse, enabling urban mining and reducing embodied carbon. Public spaces and streets are redesigned as water-sensitive infrastructures using permeable surfaces, tree trenches, and retention zones to manage stormwater. District heat networks integrate renewable and recovered energy, while ecological corridors improve biodiversity. Amsterdam's approach highlights the importance of coordination between governance, design, and technical standards. Multidisciplinary planning and design teams influence both form and function by shaping multifunctional spaces that support infiltration, cooling, and ecological performance. Ultimately, Amsterdam demonstrates that circular district design requires integrating physical loops with policies, incentives, and monitoring frameworks. Portland's Green Streets program exemplifies how distributed hydrological systems can collectively create district-scale loops. Instead of relying solely on underground pipes, Portland redesigned curbs, street edges, and intersections to integrate bioswales, rain gardens, and permeable pavements. These systems capture stormwater where it falls, filtering it through vegetation and soils before it infiltrates or enters the drainage network. This reduces combined sewer overflows and significantly improves neighborhood microclimates. Portland's success stems from strong community involvement. Residents help maintain planted areas, participate in monitoring, and contribute to stewardship programs. The district's regenerative performance emerges from the synergy of physical interventions and civic culture. As a result, Portland has become a reference point for cities seeking to transform everyday streetscapes into hydrologically functional and socially vibrant infrastructures. Singapore illustrates how high-tech and nature-based systems can operate together to form closed water loops at a metropolitan and district scale. NE Water, the city-state's reclaimed water program, treats wastewater through microfiltration, reverse osmosis, and ultraviolet disinfection before redistributing it for industrial, commercial, and potable uses. This dramatically reduces reliance on imported freshwater. Complementing this engineered loop, the ABC Waters program transforms drainage canals into ecological landscapes, integrating wetlands, vegetated slopes, and public spaces. These interventions improve infiltration, biodiversity, recreation, and water quality while reinforcing watershed identity. Singapore's regulatory environment supports integration between engineering, urban design, and ecological planning, ensuring that ecological performance is not an afterthought but a core design driver. The result is a resilient system where water circulates across technological and ecological pathways. Hammarby Sjöstad represents one of the most comprehensive examples of district-scale closed-loop implementation. Its eco-cycle model integrates water, waste, and energy systems so that byproducts from one process feed another. Organic waste becomes biogas for heating and transport. Treated wastewater contributes to district heating, and stormwater flows through a sequence of green roofs, swales, and wetlands before reaching the lake. The district's public spaces are designed as ecological infrastructures, ensuring that hydrological and biological processes remain visible and functional. Hammarby demonstrates the value of conceptual integration. Loops are not added as separate features, but planned as interdependent systems shaping the identity and performance of the district. This case illustrates how regenerative design can transform urban development into a living metabolic system. Kalundborg is widely recognized as the world's most successful example of industrial symbiosis and provides an important reference for understanding closed-loop systems at the district scale. Although not primarily a residential district, Kalundborg demonstrates how resource flows between multiple actors can form tightly integrated loops that dramatically reduce waste and environmental impact. Waste heat from the Asnæs power station is used to heat homes and supply industrial processes, while materials such as gypsum, steam, and treated wastewater circulate among partners. These interconnected flows reduce extraction, emissions, and operational costs. From a regenerative perspective, Kalundborg exemplifies how loops operate best when motivated by mutual benefits, long-standing cooperation, and transparent governance. The model highlights opportunities for applying similar principles within urban districts, particularly those with mixed land uses, where material and energy exchanges could replace linear systems and support ecological outcomes. Utrecht has become a leading European example of integrating blue-green infrastructures at the district scale. Projects such as the Merwede Canal Zone and the broader Sponge City strategies aim to absorb, retain, and slowly release stormwater, thereby reducing pluvial flooding and restoring hydrological cycles. The city systematically replaces impermeable surfaces with permeable pavements, bioswales, and green corridors that connect ecological habitats while improving microclimate conditions. Utrecht's approach demonstrates how hydrology can shape urban form by embedding water logic into street layouts, open spaces, and redevelopment plans. Rather than treating stormwater as a problem, the city positions it as a structuring resource that enhances biodiversity and public life. For landscape architects, Utrecht illustrates the value of designing with water as a fundamental organizing principle, ensuring that ecological and social functions reinforce one another. Mesoscale systems are particularly powerful because they operate at the interface where most people experience ecological processes in daily life. Streets, pocket parks, courtyards, and green corridors become tangible demonstrations of how a district manages water, heat, and habitat. Their visibility fosters public understanding and acceptance of regenerative strategies, which is critical for long-term stewardship. In many European examples, mesoscale interventions emerged from broader municipal agendas promoting climate adaptation, but their success depended on design sensitivity to local conditions, soil structure, rainfall patterns, vegetation types, and community preferences. These systems also tend to be modular and replicable, allowing cities to scale regenerative functions incrementally. As such, meso-scale projects often act as proof-of-concept laboratories, where new hydrological and ecological ideas are tested before being integrated into district-wide policies. Additionally, meso-scale systems serve as important connectors between highly engineered macro-scale infrastructures and fine-grained micro-scale interventions. They provide spatial continuity, ensuring that ecological flows, such as water infiltration, species movement, and evaporative cooling, extend across neighborhood boundaries rather than remaining confined to isolated sites. Their collective impact can significantly influence urban microclimates, reduce local flood risk, and strengthen social cohesion by creating accessible, multifunctional public spaces. As cities increasingly confront climate uncertainty, meso-scale networks offer flexible, adaptive frameworks capable of absorbing shocks while maintaining everyday functionality. Their iterative nature allows municipalities to evaluate performance, refine designs, and build public trust before committing to larger system-wide transformations. In this way, meso-scale interventions play a pivotal role in embedding regenerative thinking into the lived reality of urban environments. Infiltration basins in Ljubljana and infiltration trenches in Malaga demonstrate how urban neighborhoods can restore groundwater recharge by directing stormwater into well-designed depressions or subsurface channels. Filter drains used in Austrian cities help stabilize runoff and improve water quality by filtering pollutants through gravel and soil systems. Retention ponds in Ljubljana provide long-term water storage, habitat creation, and recreational value, illustrating multifunctionality. Detention ponds in Korugo capture peak flows during heavy rainfall and slowly release water, reducing flood risk while providing flexible open space. These interventions show how meso-scale systems can stabilize hydrological cycles and improve microclimate conditions. They also reveal that infiltration and retention, when combined, create robust layers of redundancy essential for regenerative district performance. Bioretention cells in Sassuolo and Turin use engineered soils and vegetation to filter stormwater, improving water quality and promoting urban cooling. Bioswales in Gdynia extend this principle linearly, transforming streets into functional ecological corridors that intercept and convey water while enhancing biodiversity and pedestrian comfort. Riparian buffers in Scandalara and Mischiwajau represent semi-natural systems that expand flood capacity, filter nutrient-rich runoff, and stabilize stream banks. These interventions are particularly effective in moderating hydrological extremes, creating habitat networks, and enhancing the ecological identity of urban districts. Together, they illustrate how meso-scale NBS integrate hydrological performance with public space design, enabling cities to evolve into regenerative, water-sensitive environments. Micro-scale closed-loop systems operate at the building or parcel scale and include extensive and intensive green roofs, rainwater harvesting elements, and other vegetated infrastructures. These systems may appear small in isolation, but their cumulative impact across a district is significant. By reducing stormwater runoff, lowering temperatures, supporting pollinators, and improving energy efficiency, micro-scale interventions contribute to the overall ecological performance of the district. Their modular nature enables flexibility. Buildings can retrofit closed-loop functions without requiring major infrastructural change. Micro-scale systems complement meso- and macro-scale strategies by ensuring that regenerative processes occur at every layer of the urban fabric. The extensive green roofs in Rennes demonstrate how lightweight vegetation systems can retain stormwater, moderate rooftop temperatures, and contribute to district evapotranspiration cycles. Intensive green roofs in Treviso and Wrocław provide deeper soils, more diverse plant species, and greater multifunctionality, ranging from habitat creation to recreational terrace spaces. These systems hold larger volumes of water and support richer ecological communities. When connected to greywater recycling or rainwater harvesting infrastructure, green roofs form micro-level loops that reduce pressure on municipal systems. As design elements, they exemplify how urban surfaces can become productive, climate-responsive layers that reinforce district-wide regenerative performance. A deeper comparison of the case studies suggests that regenerative districts are most successful when they couple ecological processes with social systems that reinforce behavioral change. For instance, Portland's community-maintained bioswales revealed that infrastructure performance is strengthened by civic culture. Utrecht's canal front transformations demonstrate how hydrological logic can become part of a city's identity, and Hammarby Sjöstad shows that making loops visible, through open channels, wetlands, and interpretive signage, fosters public understanding of ecological cycles. The comparison also reveals the importance of time. Kalundborg evolved gradually over several decades, illustrating that closed-loop systems mature through iterative adjustments rather than singular design interventions. Across contexts, the strongest districts are those that support redundancy, operational flexibility, and cross-scalar learning, where insights from micro and mesoscale experiments inform citywide policy evolution. This reinforces the notion that regenerative districts function as adaptive socio-ecological systems. Closed-loop district design demands a shift from creating isolated interventions to shaping integrated ecological infrastructures that function across scales. Practitioners from diverse fields, including urban planners, architects, engineers, ecologists, social scientists, and community organizations, must collectively understand hydrology, soils, vegetation dynamics, and material cycles, translating these insights into coherent spatial and infrastructural strategies. Designing with water as a guiding principle redefines the arrangement of streets, open spaces, building interfaces, and public amenities, producing urban forms that respond dynamically to environmental processes. Multifunctionality becomes essential. Urban landscapes and infrastructures must simultaneously manage stormwater, regulate temperature, support biodiversity, accommodate mobility, and foster social interaction. Achieving this requires interdisciplinary collaboration, where technical expertise, policy frameworks, and community knowledge converge to maintain and adapt closed-loop systems over time. Long-term success depends not only on design quality but on governance structures, stewardship models, and continuous monitoring that ensure ecological and social performance improves as conditions change. By embracing systemic thinking and shared responsibility, urban professionals can co-create resilient districts that operate as regenerative metabolisms, places where natural cycles are restored, resources circulate efficiently, and built environments enhance rather than diminish ecological capacity. Closed-loop district design transforms urban areas from resource-intensive systems into regenerative landscapes where water, materials, and energy circulate through interconnected loops. Macro-scale cases demonstrate how cities integrate circular strategies into infrastructure and governance. Mesoscale examples reveal the power of NBS to restore hydrological processes at the neighborhood level. Micro-scale systems show how buildings contribute to the district's ecological function. Together, these layers illustrate how regenerative districts emerge from coordinated interventions that align ecology, infrastructure, and community. Case studies show that closed-loop design is not theoretical. It is already being implemented globally, providing actionable models for future practice. Looking ahead, closed-loop district design will become increasingly central to climate adaptation and resource resilience. As extreme weather events intensify, districts capable of retaining water, controlling heat, and circulating materials internally will hold strategic advantage. Emerging digital tools such as material flow modeling, real-time hydrological monitoring, and nature-based performance indicators will enable more precise evaluation of regenerative outcomes. These tools will require coordinated engagement from multidisciplinary planning and design teams who can interpret data, understand ecological processes, and translate insights into adaptive strategies.